We are on episode number 40, and I'm going to be answering this question for y'all. How to measure the coupling factor with modal analysis. Now, we know modal analysis, FEA, analysis of ultrasonic transducers. Modal analysis is particularly useful to get the resonance frequency. But then we say, okay, now in order to get the coupling factor, or at least what we expect it to be, or what we think it should be, or theoretically could be, at least the maximum, we then use harmonic analysis, where you kind of plot your impedance. There's so many frequency points. It's kind of annoying. You're always like skipping points and stuff, or you're just trying to really optimize your model. You know, harmonic analysis solves in hours. Modal analysis, that same model will solve in minutes or less, and you'll get very specific information, all of it which is useful. Harmonic analysis, you get a lot of information, a little bit which is useful, really time consuming. So what if, you know, how would you feel if I told you that you can do a lot of what you can in harmonic analysis and modal analysis if you know what you're doing? How would that make you feel? Well, however that is, I'm going to explain it to you, and you will feel that way at the end of this video. So let's continue. This is exciting. You don't want to miss it. You don't want to stop the video here. So what is modal analysis? Modal analysis, a finite element, you know, you chop up your model, you know, the programs chop up your model in a bunch of little pieces and elements and connect them together, mass springs, whatever. But basically what you get out of it, as many of you know already, is natural frequencies of your system. And you also get a relative displacement, which is also called a mode shape. So you know that your transducer resonates at 23 kilohertz, 46 kilohertz, 35, and you know that for certain modes, there's a maximum displacement at the tip. You know, for certain modes, there's nodal points at different locations. All of that are things that you know. And then obviously you can alter the size and the shape of your transducer, and thereby alter this performance behavior in order to optimize your transducer. But that still doesn't give you the coupling factor. So let's just talk about what the coupling factor is first. Very brief introduction. I've talked a lot about it, and I will continue to talk about the coupling factor today and forever, and previous videos if you're interested in that topic. So, but what is a coupling factor? Well, quite literally, or the way you measure it, is the frequency separation between resonance and anti-resonance. There's a ratio which gives you the coupling factor calculation. Now, the physical significance of any parameter is not the method of calculation. The physical significance of any parameter is its actual physical significance. So it quite literally is the ratio between input energy and converted energy in a system. So you input electrical energy and you get output mechanical. However, this doesn't account for it's different for a resonating system. You can compare the mechanical capacitor and the pure electrical capacitor, for example, in a BVD circuit. That's going to give you an understanding. So we're not talking about like accumulation of energy. We're talking about the energy input per cycle and the energy stored per cycle, or the energy input per cycle in terms of electrical, and that much which is converted into mechanical, but not the resonation, if that's even a word. It could be. So that's the coupling factor, but again, we need that frequency separation. That's typically the way we calculate it, and that's the way it's represented. So how do we get there? And with modal analysis, and modal analysis is purely, it's purely mechanical. You just get frequencies and displacements out of it. You don't even get currents or voltages. Like, how do you do that? I'll tell you. So keep watching. Frequency separation. This is okay. So this is super important to understand. When you measure the ultrasonic transducer's impedance response over frequency, y-axis impedance, x-axis frequency, you have two resonant areas: the short circuit resonance, which is the domination by the LCR, and the open circuit resonance, which anti-resonance, which is the resonance between the electrical and mechanical parts of the system, which causes very small amount of current to flow through, except that which is needed to maintain oscillation. So we have these two different resonances. So actually, the short circuit resonance is basically a controlled voltage resonance. That's for the most applications, or most people, that's how they think about the resonance of an ultrasonic device. The anti-resonance you can actually get by, let's say you're driving your transducer at resonance, you disconnect the terminals. You'll get that oscillation frequency will immediately jump to the anti-resonant frequency, and that frequency is higher than the resonance, because now when your piezo is expanding, it's also generating charge and keeping that charge on the we generate charge in short circuit as well. That's why you have current, but this charge has nowhere to go, so it's like stored mechanical energy. So it's an extra energy storage division or area, and that makes the piezo, one way to think about it, makes the piezo stiffer. So therefore, that resonant frequency is necessarily higher than that anti-resonant frequency is necessarily higher than the resonance frequency. So we've understood that, look, in certain electrical conditions, we can generate an open circuit, like you disconnect the terminals, or other methods, like if you did an impulse on your transducer and you allowed it to just allowed that step response to kind of take place and let the system decay at the natural frequency. If you have an open circuit condition, you're just measuring voltage with a voltage probe. You don't have the terminals connected, as in a short circuit or a controlled voltage case. You, my friend, will then have a open circuit resonance. You measure a little bit higher frequency. Now is the meat. How do we find that anti-resonance? We are so aware of how to find the resonance frequency with modal analysis. We are so unaware of how to find the anti-resonant frequency, but it's so not too tough. You have to make assumptions like we always do. Assumption number one that we make is, the FEA model represents reality. That's a wrong assumption. So as long as we're doing wrong assumptions, let's continue on that path, and we'll have a good time doing it. And as long as it makes a little bit of sense and we can make a little bit of progress with it. So here's these two models that you use. Model number one is the typical one, where you model the modulus of your PZT, of your piezo ceramic, with a constant electric field short circuit parameter. So that's the not S11, this is S33, sorry, S33, under constant electric field, or you inverse that to get your modulus, and you have your whole, you can do isotropic calculations or simulations. I might get into that later, but let's just talk in general that we have an anisotropic material property. But the one you want to focus on is your modulus. That's going to be the one which is going to change the resonance frequency. So that's how you measure resonance. You compute your modal analysis, and you get frequencies and mode shapes. Perfect. So you go and you find the mode shape, the frequency that you want. You find the frequency that you want. You say this 40.3 kilohertz. That's you see the maximum displacement at the tip, and you see the nodal point close to the piezo. So okay, this is the right one. Let's continue. So then you construct a new model, and you have new material properties. In this case, it becomes more useful to model your piezo as an isotropic material. Modeling your piezo as isotropic, that is fundamentally not true, but it can be useful. So like what the saying goes, like all models are false, but some are useful. This is useful. So if you model your piezo as isotropic, because right now we're focusing on efficiency of the model, we're focusing on modal analysis, so you get results today, not several weeks from now. And the iteration process is really important to be able to keep up with your, a person may think that finite element analysis is so much faster than doing things in the lab, and that's actually not true, because how complex it can get, how quickly. But the lab results will always take the same amount of time, but you can get stuck up in like things not converging or mesh count. But in the lab there's no mesh count. You just build it, test it, works or doesn't work. You don't get too much more information out of it, that's true, but you can definitely say if it works or it doesn't work. So it can be challenging. So you want to make your models efficient to keep up with those folks in the lab, or you're going to be left behind. Or if this person's you probably just give up on models. Okay, so the second part is, let's say you model it isotropically, or even anisotropically. If you come up with the equivalent matrix for a constant electric displacement, which is the open circuit condition. You come up with the whole matrix, or if you're doing isotropic assumptions just for understanding and analysis, you would obviously have to make those properties according to your according to what mode of operation you're using. If you're using an S11 or using a 1-1 mode, you're not going to be, or 3-1, you're not going to be substituting the wrong property in there. You're going to be looking at the property which is going to dominate your device most. So you can convert that into constant electric displacement from constant electric field through the coupling factor, and those are usually given on the data sheet. So that can be an easy calculation to do. Now, the caveat here is there's assumptions, like there always is in life. So the assumption here is the stress or strain in the piezo is relatively constant. That would allow you to do this method. If you have a lot of variation of stress in your piezo, it's not going to work. Or if your piezo ceramic is basically the entire transducer, that may partially work, but you'll have to check those assumptions and see how accurate they are. But you'll still get going somewhere. You'll have an idea. So this video was about how to calculate the coupling factor. You can do it using modal analysis. Models are incorrect anyway, so just make assumptions to make your life easier, but make sure you're getting useful stuff out of it at the same time. And you will get useful stuff because you'll be able to tune your model accordingly. You'll be able to compare experiments in real time instead of like waiting a week or so. The other thing I wanted to mention was, well, this is really powerful, and it will allow your modal analysis to go to the next level. So once you do that in Model 2, so you have Model 1 frequency, that's a resonance. Model 2 frequency, that's anti-resonance. You just put your traditional coupling factor equations together, the separation of frequency squared divided by the anti-resonance frequency, or I think it was the resonance. Anyways, you have those equations somewhere in your notebook, or accessible everywhere online. So that is how you would actually get a coupling factor. Now you can do optimization for nodes. You can see which devices will provide a better coupling factor, frequency separation, which you kind of should expect. If you get something wildly different in practice, you kind of look for assembly defects or other areas that would indicate how to improve that property. So you have been watching the Piezo SHOCK Show, episode number 40. It's been great. So let's continue. I'll see you tomorrow, and be sure to check out the links for notes on this video, to subscribe to my email list, which will also get you emails on these videos every day. You'll get the presentation notes to see if you want to really dive in, which you always should be wanting to, but I can understand. People have other priorities. So I'll be here nonetheless. So you'll get that in your email, and also you can check out my services and offerings. I'm an ultrasonic transducer consultant. I provide support for companies developing ultrasonic transducers, helping them make decisions like this, like should we delve into harmonic analysis or should we just stick in modal? Modal has a lot of juice in it. People don't realize it. So I'm here to bring that to you today for everyone. But if you need some specific advice, you need somebody to work hand in hand, or at least advise you, then contact me now. Follow the links. All right, thank you, and see you next time.